Merhaba arkadaşlar. Umarım iyisinizdir. Artık dönemin sonuna yaklaşıyoruz. DDAC'lardan, hafızadan, memoriden ve mass storage'den bahsedeceğiz. DDAC'ların ardından memory, main memory ve virtual memory olarak iki parçada inceleyeceğiz. Ve son olarak mass storage yönetiminden bahsedip dönemi kapatacağız. Deadlock'larla başlıyorum. In a multi-programming environment, several threads may race for a finite number of resources, as we already know. A thread requests resources. If the resources are not available at that time, the thread enters a waiting state. Sometimes a waiting thread can never again change state because the resources it has requested are held by other waiting threads. This station is called as a deadlock. We discussed this issue actually briefly in previous chapters as a form of liveness failure. In there, we defined deadlock as a station in which every process is a set of processes is waiting for an event that can be caused only by another process in the set. In this chapter, we're going to describe methods that application developers as well as operating system programmers can use to prevent or deal with deadlocks. Although some applications can identify programs that might deadlock, operating systems typically do not provide deadlock prevention facilities, and it remains the responsibility of programmers to ensure that they design deadlock-free programs. A system consists of a finite number of resources to be distributed for a number of racing threads. The resources may be partitioned into several different types or classes, each consisting of some number of identical instances. For example, CPU cycles, files, and I/O devices, such as network interfaces and DVD drivers, are examples of resource types. If a system has 4 CPUs, then the resource type CPU has 4 instances. Similarly, the resource type network may have 2 instances. If a thread requests an instance of a resource type, the allocation of any instance of the type should satisfy the request. If it does not, then the instances are not identical and the resource type classes have not been defined properly. Under the normal mode of operation, a thread may utilize a resource in only the following sequence: request, use, and release. Request means the thread requests the resource. If the request cannot be granted immediately, for example, let's say if a mutex lock is currently held by another thread, then the requesting thread must wait until it can acquire the resource. The second one is use. That means the thread can operate on the resource. For example, if the resource is a mutex lock, the thread can access its critical section. And the last one is release. The thread releases the resource after using it. To illustrate a deadlock state, we refer back to the dining philosopher's problem from the last chapters. In this station, resources are represented by chopsticks. If all the philosophers get hungry at the same time and each philosopher grabs the chopstick on her left, there are no longer any available chopsticks. Each philosopher is then blocked and waiting for her right chopstick to become available. So this station can be described as a deadlock. A deadlock station can arise if the following 4 conditions hold simultaneously in a system: mutual exclusion, hold and wait, no preemption, and circular wait. If we hold these conditions simultaneously, that means we can characterize a deadlock. Let's start with mutual exclusion. At least one resource must be held in a non-shareable mode. That is, only one thread at a time can use the resource. If another thread requests the resource, the requesting thread must be delayed until the resource has been released by the previous one. And the second one is hold and wait. A thread must be holding at least one resource and waiting to accrue additional resources that are currently being held by other threads. Third one is no preemption. Resources cannot be preempted. That is, a resource can be released only voluntarily by the thread holding it after that thread has completed its task. You cannot force that thread to release its resources. And the last one is circular wait. A set of, let's say, P0, P1 to Pn of waiting threads or waiting processes must exist such that T0 or P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, and Pn-1 waiting for a resource held by Pn, and Pn is waiting for a resource held by P0. So here we have a circular waiting list. Every process or every thread is waiting the previous thread to release its resources. So we emphasize that all four conditions must hold for a deadlock to occur. The circular wait condition implies the hold and wait condition. So the four conditions are not completely independent. However, we shall see in the next sections that's useful to consider each condition separately. Deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. This graph consists of a set of vertices V and set of edges E. The set of vertices V is partitioned into two different types of nodes. T or P, T for thread and P for processes. Actually, I'm using these threads and processes interchangeably in this manner. So while discussing this resource management, T and P stands for the task actually. It could be a thread, it could be a process. I'm using that words interchangeably, so you can assume that in this case, thread and process are same thing in just in that manner. So the set of vertices V is partitioned into two different types of nodes, P and R. Here P, P1, P2 to Pn, the set of consisting all the processes in the system, and R from R1 to Rm is the set of consisting of all resource types in the system. So we have vertices, we have edges. On the vertex side, we have processes and we have resources. A directed edge from process I to resource Rj is denoted by Pi to Rj, like here with an arrow. It signifies that process Pi has requested an instance of resource type Rj and is currently waiting for the resource. A directed edge from resource type Rj to process Pi is denoted by Rj to Pi with an arrow like that. It signifies that an instance of resource type Rj has been allocated to thread. So this is the request edge, this is the assignment edge. That means process I requested an instance of resource J, and this means an instance of resource J is assigned to process I. So here, how we can use vertices and edges to create a resource allocation graph. Here we have a graphical example. So basically, graphically, we represent each process Pi as a circle and each resource type Rj as a rectangle. So these are our threads or processes, and these are our resources. So the resource allocation graph shown in here shows us the following situation. The sets T, R, and E. So we have threads, we have resources, and we have ads. We have T1, T2, and T3, three threads, and we have R1, R2, R3, and R4 as our resources. Also, we have some ads from T1 to R1, T2 to R3, R1 to T2, R2 to T2, R2 to T1, and the last one, R3 to T3. So also, as you can see, we have in some cases we have more than one instances for every resources. So that dots actually specify the number of instances for that resource. So we have one instance of resource type R1, two instances of resource type R2, one instance of resource type R3, and three instances of resource type R4. Also, we have thread states here. Thread 1 is holding an instance of resource type R2 because from resource to thread and edge means that instance is assigned to T1. Also, it's waiting for an instance of resource type R1 because an arrow from a process or thread to resource means that thread requested an instance of R1. So let's move on. T2. Thread 2 is holding an instance of R1 and an instance of R2 and is waiting for an instance of R3. And thread 3 is holding an instance of R3 and is not waiting for another additional resources. So given the definition of resource allocation graph, it can easily be shown that if the graph contains no cycles, that means no thread in the system is deadlocked. In the graph does contain a cycle, then a deadlock may exist. If each resource type has exactly one instance, then a cycle implies that a deadlock has occurred. If the cycle involves only a set of resource types, each of which has only a single instance, then that means we have a deadlock. Each thread involved in the cycle is deadlocked in that case. So in this case, in our case, a cycle in the graph is both a necessary and a sufficient condition for the existence of deadlock. If each resource type has several instances, then a cycle does not necessarily imply that a deadlock has occurred. In this case, a cycle in the graph is a necessary but not a sufficient condition for the existence of deadlock. Okay, so we have a resource allocation graph. We are looking for the deadlocks. If we have one instance for every resources, a cycle means, okay, we have a deadlock. But in some cases where we have more than one instances, still we can get a cycle, but that cycle does not directly imply that, okay, we have a deadlock here. We have to check the other conditions too. Here, to illustrate this concept, we are going to return to the resource allocation graph. Suppose that thread T3 here requests an instance of resource type R1, R2. So this is the difference between these one. In this example, T3 is holding an instance of R3, but it's not requesting anything. Here, T3 is actually one instance of R3 is assigned to T3. Also, T3 is waiting for an instance of R2. So since no resource instance is currently available, here we have an request edge from T3 to R2. At this point, we have two cycles exist in the system. Here we have T1, R1, T2, R3, T3, R2. We have a cycle here. Also, we have T2, R3, T3, and R2. Also T2 again. So we have two cycles here. So we can directly say that threads T1, T2, and T3 are deadlocked. Thread 2 is waiting for the resource R3, which is held by thread T3. T3 is waiting for either thread 1 or thread 2 to release resource R2. In addition, thread 1 is waiting for thread 2 to release resource R1. So every thread here, T1, T2, and T3, is waiting another thread to release its resources. So we can directly say that, okay, we have a deadlock station in this case. So using a resource allocation graph, we can easily understand if there is a deadlock here or not. If we have single resources or if we have a small set of vertices here. Here we have another example. Now consider that the resource allocation graph is like in this figure. In this example, we also have a cycle from T1 to R1 to T3 to R2 to T1 here. We have a cycle here too. However, we don't have a deadlock here. There is no deadlock in this graph. Please observe that T4 may release one instance of R2. Okay, T4 is using one instance of R2, but it's not requesting another resources. So that means in some point, T4 is going to release that instance. So in that case, T3 can use that instance. So that means T3 has satisfied, it get the requested resource from R2 and R1. So it can, after the execution, it can release that instance of R1 and R2. So based on that, we can break the cycle. So from here, from the beginning, if T4 release the instance of R2 and if T3 can use that, that means we have break the cycle. So actually we don't have any cycle path in this graph, and that means, okay, we have some cycle at the initial condition, but that does not mean we have a deadlock here. So we have to be careful about considering the cycles and deadlocks. In summary, if a resource allocation graph does not have a cycle, then the system is not in the deadlock state. If there's a cycle, then the system may or may not be in the deadlock state. This observation is important when we deal with the deadlock problem. Okay, so if no cycles means we don't have deadlock. If we have cycle, there may be or may not be deadlocks. We have to make an observation based on that. Generally speaking, we can deal with the deadlock problem in one of three ways. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlock state. We can allow the system to enter a deadlock state, detect the deadlock, and recover. And last one, we can ignore the problem altogether and pretend that deadlocks never occur in the system. So these are the three ways how we can handle deadlocks. To ensure that deadlocks never occur, the system can use a deadlock prevention or a deadlock avoidance method. Deadlock prevention provides a set of methods to ensure that at least one of the necessary conditions cannot hold. These methods prevent deadlocks by constraining how requests for resources can be made. And deadlock avoidance requires that the operating system be given additional information in advance concerning which resources a thread will request and use during its lifetime. With this additional knowledge, the operating system can decide for each request whether or not the thread should wait. To decide whether the current request can be satisfied or must be delayed, the system must consider the resources currently available, the resources currently allocated to each thread, and the future requests and release of each thread. As we noted, for a deadlock to occur, each of the 4 necessary conditions must hold. By ensuring that at least one of these conditions cannot hold, we can prevent the occurrence of a deadlock. We elaborate on this approach by examining each of the 4 necessary conditions. Let's start with mutual exclusion. The mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources do not require mutually exclusive access and thus cannot be involved in deadlock. To ensure that the hold and wait condition never occurs in the system, we must guarantee that whenever a thread requests a resource, it does not hold any other resources. One protocol that we can use requires each thread to request and be allocated all its resources before it begins execution. So that means before the execution, you have to accrue all resources. If you cannot accrue your resources, you have to wait without execution. So if you're not executing that thread, that means we don't have any deadlock at that point. This is, of course, impractical for most applications due to the dynamic nature of requesting resources. We cannot guarantee that a thread is going to request all resources at a definite point. An alternative protocol allows a thread to request resources only when it has none. A thread may request some resources and then use them. Before it can request any additional resources, it must release all the resources that's currently allocated. So this is another method. The third necessary condition for deadlocks is that there be no preemption of resources that have already been allocated. To ensure that this condition does not hold, we can use a protocol like that. If a thread is holding some resources and requests another resource that cannot be immediately allocated to it, then all resources the thread is currently holding are preempted. In other words, these resources are implicitly released. The preempted resources are added to the list of resources for which the thread is waiting. The thread will be restarted only when it can regain its old resources and as well as the new ones that's requesting. The 3 options presented thus far for deadlock preventions are generally impractical in most situations. Theoretically, okay, we can prevent mutual exclusion, hold and wait, or no preemption, but these methods are generally not practical. However, the fourth one and the final condition for deadlocks, which is circular wait condition, presents an opportunity for a practical solution by invalidating one of the necessary conditions. One way to ensure that this condition never holds is to impose a total ordering of resource types and to require that each thread requests resources in an increasing order of enumeration. So based on that, okay, it's hard to prevent mutual exclusion based on resources, hold and wait condition based on the nature of threads or processes, and no preemption. But we can prevent circular wait. Deadlock prevention algorithms, as we discussed, prevent deadlocks by limiting how requests can be made. The limits ensure that at least one of the necessary conditions for deadlock cannot occur. However, possible side effects of preventing deadlocks by this method are low device utilization, and reduced system throughput. An alternative method for avoiding deadlocks is to require additional information about how resources are to be requested. The various algorithms that use this approach differ in the amount and type of information required. The simplest and most useful model requires that each thread declare the maximum number of resources of each type that it may need. So when a thread starts execution, it's going to let's say we have resources A, B, and C. I need 3 instances of A, I need 4 instances of B, and I need let's say 2 instances of C. So based on that information, we can create an deadlock avoidance mechanisms. Given this additional information, it's possible to construct an algorithm that ensures that the system never enters a deadlock state. A deadlock avoidance algorithm dynamically examines the resource allocation state and to ensure that a circular wait condition never exists. The resource allocation state is definitely by the defined by the number of available and allocated resources and the maximum demands of the threads or processes. In the following sections, we are going to explore two deadlock avoidance algorithms. Let's continue with safe state. A state is safe state if the system can allocate resources to each thread up to its maximum in some order and still avoid a deadlock. Sorry. In a more formal definition, a system is in a safe state only if there exists a safe sequence to allocate resources to all threads or processes. Let's assume that a sequence of processes P1, P2 to Pn is a safe sequence for the current allocation if for each Pi the resource request that Pi can still can be satisfied by the current available resources plus the resources held by all Pj with j is less than I. So in this situation, if the resources that Pi needs are not immediately available, then Pi can wait until all Pj have finished. When they have finished, Pi can obtain all of its needed resources, complete its designated task, return its allocated resources, and terminate. When Pi terminates, Pi plus 1 can obtain its needed resources, and so on. So if no such a sequence exists, then the system state is said to be unsafe. If we cannot find a sequence that we can give the necessary resources to waiting processes or waiting threads, that means we are on an unsafe state. A safe state is not a deadlock state. Conversely, that a deadlock state is an unsafe state. Not all unsafe states are deadlocks, however, and an unsafe state may lead to a deadlock. So this is the let's say relationship between safe states, unsafe states, and deadlocks. As long as the state is safe, the operating system can avoid unsafe states. If we can avoid unsafe states, we can guarantee that we are not going to get a deadlock state. In an unsafe state, the operating system cannot prevent threads from requesting resources in such a way that a deadlock occurs. The behavior of the threads controls unsafe states. Okay, based on the concept of a safe state, we can define avoidance algorithms that ensure the system will never deadlock. Actually, the idea is simple. We're going to basically ensure that the system will always remain in a safe state. Initially, the system is in a safe state. We are going to assume that initially we are on the safe state and we are going to try to find a path. We are going to find a sequence to execute the waiting threads or waiting process while staying on the safe state. Whenever a thread requests a resource that is currently available, the system must decide whether the resource can be allocated immediately or the thread must wait. The request is granted only if the allocation leaves the system in a safe state. We have two methods in this case. If we have single instance of a resource type, we can use a resource allocation graph. If we have multiple instances of resource types, we have to use the banker algorithms. Let's start with resource allocation graph. If we have a resource allocation system with only one instance of each resource type, we can use a variant, a type of the resource allocation graph for deadlock avoidance. In addition to the request and assignment edges, we already used the request edges and assignment edges between threads and resources. Here, in addition to that, we are going to use another edge called as a claim edge. A claim edge from process I to RJ indicates that the process PI may request resource RJ at some time in the future. So it's not directly requesting now. It's not get claimed. It's not that resource is not assigned that process yet. But we know that that process can request that instance in the future. This edge resembles a request edge in direction, but it's represented in the graph by a dashed line. Instead of a solid line, we are going to draw that claim edge with a dashed line. When thread TI request or process PI requests resource RJ, the claim edge from process I to RJ is converted to a request edge. Similarly, when a resource RJ is released by process I, the assignment edge RJ to process I is reconverted to a claim edge. So note that the resources must be claimed a priori in the system. So that means we need prior information. We need some additional information to use that scheme. So that's before process I starts execution. All its claim edges must already appear in the resource allocation graph. Before the execution of process I has to declare that, okay, I'm going to use that resources in the future. So based on that, we can draw our claim edges. And then we can relax this condition by allowing a claim edge from PI to RJ to be added to the graph only if all the edges associated with process I are claim edges. Here we have an example. So assume that we have a resource allocation graph like that. So in that case, we are assuming that thread 2 requested R2. So actually these are claim edges. These are, as we already know, that these are request and assignment edges. And these dashed lines means T1 may need an instance of R2 in the future and T2 may need an instance of R2 in the future too. So suppose that T2 requests R2. Although R2 is currently free, we cannot allocate it to T2 since this action will create a cycle in the graph. So based on that, we can detect the cycles before they occur. A cycle, as mentioned, indicates that the system is in unsafe state. If T1 requests are 2 and T2 requests are 1, then a deadlock will occur here. As a summary, suppose that process PI or thread TI requests a resource RJ. The request can be granted only if converting the request edge to an assignment edge does not result in the formation of a cycle in the resource allocation graph. If that conversion is going to create a cycle, you are not going to allow that thread to claim, actually assign that resource. So based on that, we can avoid unsafe states. That means we can avoid deadlocks. The resource allocation graph algorithm is not suitable to a resource allocation system with multiple instances of each resource type. If you have one instance for every resource type, okay, you can directly use the resource allocation graph to avoid deadlocks. But if you have more than instances in your resource types, you have to use another algorithm. The deadlock avoidance algorithm that we described next is suitable to such a system, but it's less efficient than the resource allocation graph algorithm. This algorithm is commonly known as the banker's algorithm. The name was chosen because the algorithm could be used in a banking system to ensure that the bank never allocated its available cash, you can assume that as resources, in such a way that it could no longer satisfy the needs of all its customers. So based on that logic, we are going to call that algorithm as banker's algorithm. When a new thread enters the system, it must declare the maximum number of instances of each resource type that it may need. This number may not exceed the total number of resources in the system. When a user requests a set of resources, the system must determine whether the allocation of these resources will leave the system in a safe state or not. If it will, the resources are allocated. Otherwise, the thread must wait until some other thread releases enough resources. Okay, we are going to continue with the details of the banker algorithms, but before that, let's take a break. I'll be here in 10 minutes.